Welcome to section 4.6, inverse trigonometric functions. In this section, we have 4 objectives. Let's start with the first one. Find the equation of the inverse of a function. So suppose a function f is defined with an equation instead of a list of ordered pairs. We obtain the equation of the inverse of f by interchanging the role of x and y in the equation for f. The inverse of a function reverses the input-output relationship of the original function. So if a function f of x takes an input x and produces an output y, then its inverse, the inverse of f of x, takes y as an input and returns x. So here are 4 steps to help us find the inverse of a function. Step number 1, we'll replace f of x with y. So we'll rewrite that function as y equals. Step 2, we'll swap x and y. So we'll interchange wherever there's an x, we're now placing it as y, and wherever there's a y, we're now writing it as x. Then we'll solve for y. So we'll isolate y to get the equation in the form of our inverse function. And then we'll verify that it's actually the inverse by taking f of the inverse of f of x and the inverse of f of x and make sure they both equal x. If they both equal x, then we know that they are inverses of each other. So let's do an exercise. If the function f is defined as f of x equals 3x plus 1, then find the equation that represents the inverse of f. Okay? So we are going to use our steps to answer this exercise. So step number 1, we're going to take f of x and we're going to replace f of x with y. That's step number 1. Step 2, we're going to swap x and y. So now I'll have x equals 3y plus 1. Then in step 3, I'm asked to solve for y. So I will subtract 1 to the other side. And then I will divide both sides by 3. And then step 4 is to verify. So our inverse function is x minus 1 over 3. Okay, so to verify, I'm going to find f of the inverse of f of x and make sure that it equals x. And I will find f, the inverse of f of x, and make sure that also equals x. So since I know that the inverse of f is x minus 1 over 3, I'm going to substitute that into my f of x function, which is 3x plus 1. So now I have 3 times x minus 1 over 3 plus 1. The 3's cancel, so I have x minus 1 plus 1. The 1 and negative 1 cancel, leaving me with just x. Next, I'm going to substitute f of x into my inverse function. So f of x is 3x plus 1. So substituting this expression into my inverse function, I get 3x plus 1 minus 1 divided by 3. So I can drop the parentheses in the numerator, which then allows me to cancel my 1 and negative 1, leaving me with 3x over 3, which equals x. Since they both equal x, I know the inverse equation, x minus 1 over 3, is the inverse of f. All right. So I'm going to switch it around a little bit, and we're going to do the third objective first, and then come back to B. So we'll look at C first and identify inverse functions, and then we'll sketch the graph. So we can distinguish between functions with inverses that are also functions and those inverses that are not. A function has an inverse if and only if it is one-to-one, and that means that each input corresponds to exactly one output, and each output corresponds to exactly one input. So to determine if a function has an inverse, we're first going to check for the one-to-one property. So a function is one-to-one if it passes the horizontal line test. That means when I graph my function and I draw horizontal lines, that horizontal line intersects the function only one time, so no more than one time. If a function is not one-to-one, then we may find restrictions in the domain in order to make it one-to-one, meaning it's one-to-one between 2 and 10. The second is to verify using function composition. So like we did in the previous exercise, you will take f of the inverse of f and the inverse of f of x. So in this case, g of x would be considered our inverse function, and you would find the composition, making sure that they both equal x. And if they both equal x, then we know that those two functions are inverses of each other. So for example, f of x equals x squared does not have an inverse over all real numbers because it fails the horizontal line test. Okay. However, if we restrict f of x to x is greater than 0, then its inverse is the inverse of f of x equals the square root of x. Okay, so just to help us visually, this is the graph of x squared. If I were to draw horizontal lines, you would see that both horizontal lines touch the graph more than one time, so it fails the horizontal line test. But if I restrict the domain to x is greater than 0, so here, then when I draw my horizontal lines, the horizontal lines only touch the graph one time, therefore I have an inverse of my function. So for trigonometric functions, we can restrict their domains so they are one-to-one, which then allows us to define their inverse functions. So now let's do objective B. Sketch a graph of a function and its inverse. So graphing a function and its inverse allows us to visualize how the two functions relate to each other. A function and its inverse are reflections across the line y equals x. So our 4 steps here are going to show us how to graph a function and its inverse. We first are going to graph the original function f of x, and we can utilize our calculator or plug in points to help us. Then we're going to draw the line y equals x, which serves as the reflection line. Then we will switch the coordinates of key points from the function f of x to plot the inverse function, the inverse of f of x. For example, if f of x passes through the point 2,5, then the inverse function is going to pass through the point 5,2. Then we'll sketch the inverse function, ensuring it reflects symmetrically across y equals x. Okay, so let's do an example together. So we're here asked to graph the function y equals x squared plus 1 and its inverse, and then give the equation for the inverse. So before we graph, let's get the equation of the inverse. All right, so let's start off with y equals x squared plus 1 So we'll interchange the x and y. Then we will solve for y. So we want to isolate y by itself. Then I'll need to take the square root of both sides. So then that gives me y by itself. So f of x equals x squared plus 1, but the inverse of f of x equals the square root of x minus 1. So we can verify that these are indeed inverses of each other. So the inverse of f of x is the square root of x minus 1. So that is what we will substitute into f of x. So we have the square root of x minus 1 squared plus 1, which will get us x minus 1 plus 1, because the square eliminates the square root. Negative 1 plus 1 is 0, which then gives us x. So next we'll take the inverse of f of x. And that means we will be substituting in x squared plus 1 into the inverse function. So the square root of x squared plus 1 minus 1, that's all under the square root. We can drop the parentheses, which will allow us to eliminate the 1 minus 1, which is 0. So we will then have the square root of x squared, which is x. So we know now that both equations, f of x and the inverse of f of x, are inverses of each other. Okay. All right. So now let's graph both functions. So we're first going to graph f of x, which is this equation right here. And we know the inverse of f of x is the square root of x minus 1. Okay. So let's get some points. You can utilize your calculator or you can just substitute in some points. I'm just going to substitute in some values, and that will then give me a y, which will then give me my ordered pair. So if I plug in -2, I'll get 5. If I plug in -1, I'll get 2. If I plug in 0, I'll get 1. If I plug in 1, I'll get 2. And if I plug in 2, I'll get 5. We'll just stop right there. Then because I know my inverse function is indeed the inverse of f of x, I can take each ordered pair and I can swap the x and y coordinates. So I'll have 5, 2, 2, -1, 1, 0, 2, 1, and 5, 2 as the coordinates for my inverse function. So on my graph, I'm going to make a dashed line of the equation y equals x, because I know both of my functions are going to be mirror images over this line. So this is y equals x. We're then going to plot our f of x function. So we'll just plot these points. I am going to label my axes so you know what I'm doing. I'm going to go by, I'm going to skip every 2. So this is going to be 1, 2, 3, 4, and 5. I'll do the same thing on the x-axis as well. So 1, 2, 3, 4, 5. Okay, so now we can plot some points. Oh, I need to do the negatives. I forgot to do that. I don't go too far into the negatives, but I'll place it here so that we can know exactly what we're plotting. Do these ones as well. So -1, 2, 3, 4, 5. All right. So we'll have -2, 5. We'll have -1, 2. We'll have 0, 1, 1, 2, and 2, 5. So this is the function of f of x. That's the graph. Now we can draw the inverse function. So we have 5, 2. We have 2, -1. We have 1, 0. We have 2, 1. And we have 5. Oh, one of these is supposed to be negative. Okay, so this is supposed to be -2. So it's supposed to be 5, -2. All right. Okay. And so that is our graph of the inverse function of f of x. Excellent. All right, so now our last objective is to evaluate inverse trigonometric functions. So inverse trigonometric functions undo trigonometric functions, returning an angle as an output instead of a ratio. These are written as arcsine, arccosine, and arctan, or alternatively as the inverse of sine, the inverse of cosine, and the inverse of tan. When you are evaluating these inverse trigonometric functions in your calculator, you will see the inverse of sine, inverse cosine, and inverse tangent as buttons on your calculator, but you most likely won't see arcsine, arccosine, and arctan. But if you see those as problems, you can always rewrite them as the inverse of the trigonometric functions. So, in understanding inverse trigonometric functions, let's note that the inverse of sine of x returns the angle whose sine is x. The inverse of cosine x returns the angle whose cosine is x. And the inverse of tan of x returns the angle whose tangent is x. So since sine, cosine, tangent are not one-to-one all over the real numbers, we restrict their domains in order to make their inverses valid functions. So this chart explains a little bit in regards to the inverse functions of sine, cosine, and tangent, what exactly they mean in terms of their equation, and then their restricted domains. So the inverse sine of x is going to equal theta because we're trying to find the angle whose measurement is x. So that means x equals the sine of y, where y is theta. The restricted domain for sine is going to be between -pi/2 and pi/2. For the inverse cosine, very similar. The inverse cosine of x equals theta. So we'll have x equals cosine y, where y is theta. And the restricted domain is between 0 and pi. And then the inverse of tan of x, also arctan, meaning x equals tan of y, where y is theta, all right, has a restricted domain similar to sine between -pi/2 and pi/2, but they can't equal their endpoints -pi/2 and pi/2, okay? So we can then evaluate in radians without using a calculator or table these three different inverse trigonometric functions. So in A, the inverse cosine of -1/2 is saying find the angle between 0 and pi, because that's the restriction, whose cosine is -1/2. Okay, so this is the same thing as the cosine of theta equals -1/2. And in this case, theta will equal 2 pi over 3. Okay, so the angle between 0 and pi, whose cosine is -1/2, is 2 pi over 3. Okay, the arcsine of -√3 over 2 can be rewritten as the inverse sine of -√3 over 2. So we're trying to find the angle, the sine of theta, that equals the √3 over 2. And the restrictions for sine are between -pi over 2 and pi over 2. So theta would be pi over 3. Okay. And then we have the inverse of tan of -√3 over 3. This means we're trying to find theta, whose tangent is -√3 over 3. So for tangent, our restriction is between -pi over 2 and pi over 2, exclusive. So theta then will be -pi over 6. Okay, and you can use the unit circle to help you if you would like. All right, so now we can use our calculator to evaluate each expression to the nearest tenth of a degree. So in your calculator, if you are using TI 83 or 84, you have right in the middle the functions sine, cosine, and tangent. But to get to their inverses, you'll have to press the second button and then sine for the inverse of sine, or cosine for the inverse of cosine, and tangent for the inverse of tangent. When you have a problem that has arcsine or cosine, just remember that's just another form of writing the inverse trig functions. So you can rewrite arcsine as the inverse of sine. You can rewrite arccosine as the inverse of cosine, and arctangent as the inverse of tangent. Okay, so why don't you pause the video and enter these expressions into your calculator, rounding to the nearest tenth of a degree. Okay, so now that you're back, you should have the following values. So for A, you should have 25.6 degrees. For B, -25.6 degrees. C, 136.2 degrees. For D, 43.8 degrees. For E, 75.3 degrees. And for F, -75.3 degrees. Okay. All right, now we're going to evaluate sine of the inverse cosine of 12 over 13 without using a calculator. Okay. So to do this, we're going to let the inverse cosine of 12 over 13 equal theta. So that means the cosine of theta equals 12 over 13. Okay? So let's use a right triangle to help visualize this. Okay? So we have theta here in the corner, and we know our formula. SOHCAHTOA helps us identify where each length is represented. So cosine is adjacent over hypotenuse. So that means the adjacent side to theta is going to be 12, and the hypotenuse is going to be 13. So that means I can find this missing side by using the Pythagorean theorem. Okay? Why do I need to find the missing side? Well, if I can identify what this missing side is, then I would be able to find sine, because sine is opposite over hypotenuse. Okay? Remember, this middle part here equals theta. So in other words, I'm trying to find the sine of theta. Okay? So let's take our Pythagorean theorem. A squared plus b squared equals c squared. I want to find b, so I'll have b squared equals c squared minus a squared. Okay? So b will equal the square root of c squared minus a squared. So b equals the square root of 13 squared minus 12 squared. Okay? 13 squared is 169. 12 squared is 144. So if you subtract those values, you'll get 25. Okay? And so b then will equal 5. Okay, because although our square root gets us both -5 and 5, we cannot have the length of a triangle be equal to a negative value. Okay, so we know b equals 5. So then the sine of the inverse cosine of 12 over 13 equals the sine of theta, and the sine of theta is adjacent over hypotenuse, which is 5 over 13. Ooh, that was fun. I had chills. All right. Okay, for our next one here, we have cosine, sine, the inverse sine of x over 2. So why don't you pause the video and give it a try? Okay, welcome back. I hope you did give it a try though. If not, that's okay. So this is very similar to the previous problem. All right, so we're going to let the inverse sine of x over 2 equal theta. So that means the sine of theta equals x over 2. Okay, so we'll use a right triangle to help us. We know TOA, and sine is opposite over hypotenuse. So that means the opposite length is x and the hypotenuse is 2. So we're trying to find this bottom length because we're trying to find cosine. Remember, this equals the cosine of theta because the inverse sine of x over 2 equals theta. So we'll use the Pythagorean theorem to help us find our missing side length. And we want to find a squared. So c squared minus b squared equals a squared. We can take the square root of c squared minus b squared, which equals a. So a equals c, which is the hypotenuse, which is 2 squared, minus b, which is x, so x squared. So then a equals the square root of 4 minus x squared. Okay. So the cosine of the inverse sine of x over 2 equals the cosine of theta, and the cosine of theta equals adjacent, which is a, which is the square root of 4 minus x squared, over the hypotenuse, which is 2. And that is the answer to our expression. And that concludes section 4.6.